In this video, we're going to look at solving trigonometric equations using a formulaic approach. And what I mean by this is we're going to examine the general solution. So it's a term that you might have heard, but hopefully we'll unpack what it means in a little bit more detail. Let's look at the graph of y equals sine x. So that's just that thing there that we've highlighted. And we can also look at the graph y equals 1/2, which is just that. So one way that we can think of solving equations is if we, the first graph, let's call it y1, if we let y1 equal y2, which is the second graph. So y1 we said was sine x, and y2 was y equals 1/2. And so you can see here that we can imagine equations as one graph equaling the other and finding the point of intersection. Now what we notice is that we've got a point of intersection here and a point of intersection there. I know that the y value is going to be 1/2. And so what I can see is that there are two x values for which this is true. They occur here and there. So it's important that we think of this as, where are these solutions occurring and how periodic is their nature. For instance, if we zoom out on the graph, here's that first and second solution, but exactly 2 pi across, we can see that it happens again. And this one happens exactly 2 pi across. This is because the period of the function sine x is 2 pi. But what we definitely know is that this distance here is certainly not equal to 2 pi. You can see that visually. It's definitely not going to be 2 pi. So we need a more formulaic way just to work these two complementary angles out. Another way we can think about this is imagining the unit circle. So I've got my unit circle here. Now we're after the y value of 1/2. Remember that sine x is always going to be the height. So 1/2 would be exactly 1/2 of the way up, like so. And so we're thinking there's one solution which is this angle, and there's another solution which is that angle. Let's call it θ2. And so this also reinforces that idea of all things are positive in this quadrant and sine is positive in that quadrant. Now, θ1 and θ2, that's actually these x values here, θ1 and θ2. And so we can imagine that our very first angle, if we use our table of values, the inverse sine of 1/2, or I could say the arc sine of 1/2, is going to be pi on 6. So that first value here is pi on 6. We know that the complementary angle occurs in the second quadrant, where we'll be saying pi minus that angle. So pi take away pi on 6 is 5 pi on 6. So we can see that we've kind of got that relationship of here's an angle, and we're also trying to find pi minus that angle, because both of those are at the same y value. I know that once I've got one, they're 2 pi apart, and I can see that here. So we're trying to use that information and put it into a formula. And it turns out it's relatively easy to do so. So although it is relatively easy to do so, we do need to consider these two separate angles as both having their own answers, and then adding a period of 2 pi. So that first angle that we mentioned, if I bring up what we thought of as our unit circle, you'll remember that there was one answer, we might call that theta, and there was also the other answer, which we might call my second theta. In our general solution, we could say, oh, okay, the first set of answers is 2n pi plus whatever value I read from the table. So remember that was, in our case, the arc sine of a half, but we'll just call it A. So that's that first one. It's simple enough. We get our first answer read directly from the table, and then we just add 2n pi. Now what is n? Well, n is an element of z. Remember that number field z, that's not a very nice way, we'll do it one more time. That number field for z is just the integers. So we're saying it's 1, 2, 3, 4, and so on and so forth. It's also equal to -1, -2. It's also equal to 0, incidentally. So it's just all those whole numbers, but it's a way of adding lots of 2 pi in either direction. Now, that makes sense, because remember that the first thing we did to find what is the arc sine of a half is we just did the arc sine of a half. We didn't worry about adding 2 pi. That's because the first value for n that we thought about was 0. So that's how we get our first set of answers, and we're just going to add a period each time to find the rest. The second set of answers is a little bit more in depth. This is going to be 2n plus 1. So this is a way of getting all the odd values of pi. Now, 2n plus 1 pi, this time it's going to be minus the arc sine of A. So why is it going to be minus? Because remember we found that complementary angle as pi minus. And so we could also do 3 pi, which would be going around again, and 5 pi. And this is a way of getting it. So it's important when we look at trying to find all the answers for sine, our general solution comes in the form of 2 different equations. One gives us the answer in the first quadrant, the other one gives us all the answers in the second quadrant. And we can just sub in values of 0, 1, 2, 3, 4 in for n in order to find the rest of the answers. So a general solution isn't really like giving us an answer, it's more like giving us a way to find any answer we want. Did we want the 52nd solution? No worries, we'll sub in 52 or 51 for n. Depends if you count 0 as the very first solution. Now the general solution for cosine is much easier. There's only one rule that we need, because the cosine is an even function. In fact, if we just sketch a little graph of this very quickly, we can see that our graph looks like this. And if I imagine a straight line and its 2 points of intersection, we'll find that this answer would have just been read from the all quadrant. So that's just going to be the arc cos of, or the inverse cos of the angle. And this one here will be in the C quadrant, which we can think of as 2 pi minus. Sorry about that. I was just saying we can think of this answer as 2 pi minus that angle. So the way it turns out, when I sub in values of n that are 0, 1, 2, 3, or 0, -1, -2, -3, I can find the complete set of these solutions simply by doing 2n pi plus or minus the arc cos of alpha, of A rather. So remember that we can think of the cosine function as an even function, so I don't have to worry about odd numbers, whereas up here with the sine graph, I had to have 1 for all the even solutions, 1 for all the odd solutions. Is one way to think of that. Now the tangent function is another one that's much easier to apply. And it's simply because tan is positive in this quadrant and in that quadrant, and that's exactly 1 period apart. We can think of this distance here as being pi on the diagonal, or 180 degrees. And so you've often heard the phrase that tan is periodic about pi, or rather the period of tan is just going to be pi. And it's so true when we are looking at finding the solution, that we can say theta is equal to n pi rather than 2n pi. And it's just going to be n pi plus the arctan of A. Remember, we can find all those backward solutions simply by imagining n to be -1, -2, -3, etc. So a couple of things just to remember. When we're finding a general solution and it involves sign, we're going to need to have two completely separate answers. One is going to look like this, and the other will look like that. We know that we need to have n is an element of z, which helps explain our answer, to tell the user of this solution that they need to sub in 0, 1, 2, 3, 4, or 0, -1, -2, -3. In other words, sub in an integer for n. If we're dealing with the cosine, well, there's just going to be one solution there. We also still need to have n is an element of z. Now I say one solution, it's because we're representing both in the form of a plus or a minus. And that relationship will hold true whether we sub in negative numbers for n, positive numbers, or 0. As long as it's an integer, that should be fine. For tan, we can also write this out in one line. However, for tan, there really is only one solution because it's periodic about pi, not 2 pi. So we can define them all just by having n pi. Keep in mind, when we give our answer like this, we have to tell the user what is n. N is an element of z. N is all the integers. So now that I've bored you all to tears, it's time to put this into practice. We're asked here to find the general solution of the equation tan x minus √3 equals 0. So first of all, I'm going to say tan x minus √3 equals 0. That's not much use to me. I want to be getting x on its own. In all those previous examples where we went through the formulas, they were all in the form of theta equals blah blah blah. So in this case, we want this to be x equals something something something. So I'd say tan x is equal to the square root of 3. And using my general solution for x is equal to n pi, so this is going to get all those various other answers, plus the arctan of √3. Now remembering here that n is an element of z. So, what is the arctan of √3? Using my table of exact values, I can see that the arctan of √3 is going to be equal to pi on 3. So this is equal to n pi plus pi on 3. Now, as long as I write n is an element of z, this is actually a correct answer. However, it's usually best practice to simplify the answer. So let's get this all over one common denominator. I can represent n pi as 3n pi on 3. That way I've got a common denominator. And now I can say x is equal to 3n pi plus 1 pi divided by 3. And if I take pi out as a common factor, I've got 3n plus 1 pi all over 3, where n is an element of z. So this is a more complete answer, and it's one that I would suggest you do. I wonder if you can't look at part B now, pause the video and give it a go. Remember, you're looking to try to get that cos on its own before you can solve anything. You can then apply the general solution by using the formula and your table of exact values, and simplify your answer right at the end. See how you go, and we'll do the answer in a moment. Okay, so for part B, in order to get that cos 2 theta on its own, we're going to say cos 2 theta is equal to, if I brought that over and divided by 2, we get √2 on 2. Remember that that's the same as 1 on √2. So it's fair to say now that 2 theta is equal to, well, we're going to need our general solution. For cosine, that's 2n pi plus or minus the arc cos of √2 on 2. Remember, the arc cos of √2 on 2 saying what angle or cosine of what angle gave me this answer. And reading from my table of exact values, that's going to be pi on 4. So I only have to take the first quadrant answer. So this is where I can absolutely just use the table of exact values. So I'm left with this odd thing where 2 theta equals 2n pi plus or minus pi on 4. Now to get theta on its own, because that's what we're trying to solve for, let's divide by 2. And so I end up with theta is equal to n pi plus or minus pi on 8. In order to get this all under one denominator, to simplify it, theta is equal to n pi plus pi. Well, this had to be 8 over 8, because I had to make this fraction 8n pi over 8. And if I take pi out as a common factor, I find theta is equal to pi outside of 8n plus 1 over 8, and I know n is an element of z. Now there's a second part to this. We did have to find the general solution. Then it says, and hence find all solutions between negative pi and pi. So this word hence is really important in our exams because it means that you have to do what it asked you first. You have to find this based on what you did there, based on what you did previously. So we had to find this general solution. But now to find the solutions between negative pi to pi, I'm going to sub in values for n and see how we go. For instance, when n equals 0, 8 times 0 plus 1 is 1. And so we get our first answer as pi on 8. So we might just think, okay, n equals 0, the answer is pi on 8. Well, when n equals 1, 8 times 1 is 8, plus 1 is 9. 9 pi on 8 is bigger than pi, so that can't work. But if n was negative 1, then we end up with negative 7 in the brackets, pi on 8. So the answer is negative 7 pi on 8. And that is in the domain. It's not further out than negative pi. So we've got two answers. We've got pi on 8 and negative 7 pi on 8. So here's another opportunity for you to pause the video and see how you go attempting to answer these questions. Remember, with sine, we're going to have two completely separate answers. All you need to do is apply the general solution once, apply the other solution, and right at the end we can add pi on 3 to everything. It's going to test your understanding of fractions a little bit, but with practice I promise you'll get it. So pause the video, give them a go. Okay, for part A, remember we can think of this as two separate answers. If I wanted to bring that sine over, or we can imagine that this is already on its own, it's already a sine of something, so to get the inside on its own, we need to do the arc sine. So we're going to say x minus pi on 3 equals the arc sine of root 3 on 2. But of course, we're after the general solution. So we need to do a little bit more than that. We need to think about that general solution. So x minus pi on 3 is going to be equal to 2n pi plus the arc sine of root 3 on 2. Now, there's also a second set of solutions, and that would be 2n plus 1 pi minus the arc sine of root 3 on 2. So there's two separate solutions here that we're going to look at, and I might split them up as such. We'll say this one will be 2n pi plus the arc sine of root 3 on 2. This will be 2n plus 1 pi. So I've just got those brackets wrong, sorry. minus the arcsine of root 3 on 2. We'll just clean this up. Now from my table of exact values, I can see that the arcsine of root 3 on 2 is going to be equal to pi on 3. So this first set of answers looks like 2n pi plus pi on 3. Now, remembering that it's not x which equals this, but in fact x minus pi on 3. And so if I want to get x on its own, I'll need to add pi on 3 to both sides. So x equals 2n pi plus 2 pi on 3. In order to get this all over one denominator, this 2 could become a 6 over 3. And so I end up with 6n pi plus 2 pi over 3. And if I take 2 pi out as a common factor, I'll end up with 3n plus 1. I'll just give myself a bit more room. There we go. 3n plus 1 over 3, where n is an element of z. So there's one complete set of answers. The other set of answers, we need to follow this, remembering that x minus pi on 3 is equal to 2n plus 1 pi minus, remember the arcsine of root 3 on 2, in this case, was pi on 3. And if I bring that minus pi on 3 over, then x equals 2n plus 1 pi minus 2 pi on 3. So now it's important to try to get this all over one denominator. So I could times this by 3 over 3, and I end up with 3 2n plus 1 pi minus 2 pi all over 3. If I expand the brackets, 6n, really 6n pi plus 3 pi, because I'm multiplying by pi as well, minus 2 pi over 3 simplifies down to pi out as a common factor. 3 pi minus 2 pi is just pi. And so I've got 6n plus 1 over 3. Now I don't have room on the screen to do this, but hopefully you'll also say n is an element of z. So there you have it. Now the question of course becomes, what does this look like in exam? Well, suppose we were asked to find the general solution for this equation. I would start first by making sure I get sine x equals something. That's what I'm looking to try to get to. So I can add 1 to both sides and divide by 2 to both sides. So that is sine of pi x on 6 is equal to 1/2. Next, I can think about my general solution. So pi x on 6 is equal to, there are two answers. One, 2n pi plus the arcsine of 1/2. So that's going to be plus pi on 6. The other one, 2n plus 1 pi minus pi on 6. Now remember that that's still equal to pi x on 6. So if I multiply both sides by 6 over pi, because multiplying by 6 over pi will cause those to cancel, then x will be equal to 2n pi, well 2 times 6 is 12 over pi, so that disappears, plus, if I'm timesing pi on 6 by 6 on pi, you can see the answer is 1. So x equals 12n plus 1. There's another solution though. If we multiply this whole thing by 6 over pi, then 6 over pi, well, the pi's cancel. 6 over pi, everything cancels down to 1. And x is equal to 6 times 2n plus 1. So x is equal to 12n plus 1. So we can see here that in fact these are the same solution this time. So all that needs to happen to finalize our answer is say x equals 12n plus 1, where n is an element of z. So we're then asked to find the largest solution. Well, let's imagine what these solutions look like. If n equals 0, 12 times 0 is 0 plus 1, x equals 1. If n equals 1, x equals 13 because it's 12 times 1 plus 1. If n equals 2, well, we'll have 12 times 2 is 24 plus 1. We get to 25. And so you can see that these are all 12 units apart. So my answers for x so far are 1, 13, 25. The next one will be 37. The next one would be 49. And the one after that would be 61. Now 61 is too big. So if we're finding the largest solution between 0 to 60, the largest solution would be x equals 49. Another common occurrence for general solutions in the exam is usually in exam 2, this is of the VCE curriculum, where you'll find a multiple choice. Now it says here the function with the rule f of x equals 4 tan pi x on 3 has a maximal domain. So what we need to think about is what is the domain of tan? Well, tan can never have an inside part of pi on 2, nor can it be a multiple or an integer multiple of pi on 2, because that's where the asymptotes occur. So the maximal domain of tan can be thought of as all the real numbers except any of the asymptotes. So we've got to think of a way that we can generally describe those asymptotes. Well, I know that pi x on 3 cannot be equal to pi on 2. That's something that I know cannot be the case. And the fact that this is 4 on the outside isn't going to change that. Remember with tan, if I imagine that graph that looks like this, if I stretch it, it's not going to change where the asymptotes are. 2 tan x has the same asymptotes as tan x. So let's go back to what I know can't be the case. Pi x on 3 can't be equal to pi on 2. But also, it's going to be a period each time. Now remember, the period is pi on n. So if I've got, my n is pi on 3, then my period is pi on 3. If I bring that up, I find that I have 3 pi on pi, which is 3. So my period here is going to be 3. If we solve this function, pi x on 3 equals pi on 2, so multiply by 3, divide by pi, and x is 3 pi on 2 pi, it's 1.5, 3 over 2. Now of course it's not just 3 over 2, it's every multiple of 3 after that. So x can't be equal to, remember everything we're talking about here is where are the asymptotes, so it's 3 on 2 plus every multiple of 3 after that. Remember that n is an element of z. Now looking at the answers here, none of them are that clear, but I do see that all of them have been simplified. So I need to try to take this here and put it over one denominator. So in other words, x can't be equal to 3 over 2 plus 6n on 2. So x can't be equal to 3 plus 6n over 2. Now I can try to take out a common factor, and x can't be equal to 3 outside of 1 plus 2n over 2. That answer is E, because we're saying x has a maximum domain of reals but not the asymptotes, and here is a general solution for those asymptotes. It's a complicated question, and there are some other easier ways to find this. There's a way that you can just memorize the general solution for asymptotes of tan, but we're going to do that a bit later. So, in summary, we need to remember that if we're dealing with sine, there are going to be two answers. There's one set and another. We know that we need to write n as an element of z because that tells the user of this general solution that we've got all the integer multiples. So we're going to be using n equals 0, 1, 2, 3, or -1, -2, -3, etc. If we're dealing with cos, we do have two sets of answers, but they're given as a plus or minus. So we really only need to remember just the one. For tan, we also only need to remember just the one, but there really is just one solution here, because it's not plus or minus, because tan is periodic about pi, not 2 pi.